transfer functions. Okay, and so that is something that we have seen. But another, so we have seen that and the output would be represented as the linear combination of two independent inputs. Output. So this is for the histogram example that we have seen. Here our output variable can be modeled as linear additive terms of two independent inputs. Here the two independent inputs are one is the heat input, other one is the inlet temperature to the system. So so we kind of addressed the first issue. So now let's look at the second issue, which is before that. So we have seen. So you might be dealing with any nth order ODE. So your system that you might, any process system that you would deal with may contain an nth order ODE, which essentially means that n is greater than m. You see. So your output side, the order is n, while the input side, the order is n, and generally n greater than m to make the system realizable. We'll see what is meant. So if you have such a system, I'm sorry. Eventually, your transfer function would be a ratio of two polynomials, one corresponding to the input side and one corresponding to the output side. And you would really see that the order of a transfer function again would be generally less order of the denominator polynomial. So again, to make it realizable, n, here the order of the denominator polynomial is n. We have to impose a condition that n should be greater than n to make the system realizable. And what is this causal thing we will talk about also later. I'm sorry. So I am not very sure how long I'll take, but I think I'll try to cover at least this part of the topic and probably stop for today. My thought is not really good. Okay, so another advantage of having transfer function is, let's say you have an input, and before it become output, before it transformed to be an output, let's say there are multiple transfer function terms in between. Okay, so I will call this U kind of operate, G1 is kind of operated on U, and I got something known as Y1. It's an intermediate output, and Y1, G2 kind of operated on Y1 to get Y. So the multiplicative rule suggests that this is a very useful rule. So your total Y you can just be computed as, okay, G1 times G2 times U, which means that you can multiply the transfer function. This is also coming from the property of superposition. And what we call algebraic properties of transfer function. This actually comes out to be a very handy tool. Why? Because G1 essentially stands for an ODE, which is converted in from the time domain. Because if you see Y by U is G1, and if you do an inverse transform, this is an ODE. The same applies there. You cannot take product of two ODEs just like that. And so let's say if you have two ODEs, for instance, okay, tau1 plus so just tau1 dy by dt plus k is equal to b. Let's say if another tau2 dy by dt plus k2, k1 here, k2 here plus p2. You cannot take them. You cannot multiply these ODEs together. While, but in the transfer function case, when you are in the Laplace domain, the multiplication of the transfer functions is allowed, and that's a valid operation. That kind of simplifies many of your what you call, if there are, if you are, let's say if you have a system. So let's say you have a system input, okay? So let's say you're feeding the reactor. So this, let's say this is like a feed processor, then let's say this can be reactor, it's like a preprocessor, some sort of cleaning or something happened. Then there is a separator, so then there is a what you call gas cleaner. You might have heard these used terms in chemical technology and so on and so forth. Yes, so there are various components there for your system, and you finally get your output. Right? Let me call it this as U, and this is your Y. So if you know the transfer functions of individual one, let's say 1, 2, 3, 4, 5, to get this forward path, let's say from U to Y, you only need to multiply. So to the overall model. So if you have independently developed model for all each of these subunits, the overall model is just a multiplied form of this individual model. So it's a very useful result. This may not be true if you are working with them in the domain of the ODE. So this is like a very useful tool. So if you have an independently developed models for the subunits, we just need to multiply them together. I'm sorry. Okay, so another possibly another so this is again a very handy rule. Another thing that you would always see is an additive rule. Let's say there are two inputs passing through two different transfer function and get summed up to get your output. So then the additive rule says that the overall output y is just u1 times g1 plus u2 times g2. So I'll tell you again an example of this sort. So let's say there are two. You're blending, okay? You have a feed U, and you make it's going to a reactor. I think you have another feed U2 that's not going to the reactor, and your product, whatever you got, you have to blend to make the final product. This is your final output. So you have two feeds that is passing through two independent reactors, and there. So this is very common. So basically, in drug manufacturing or even petroleum, most of the time. So because you have multiple excipients which has to pass through independent operations, and you mix them together to get your final outputs. So here also this is a very useful operation. U2 times, so if the transfer function of, let's say this is G1 and this is G2, U2 is written right for G2 and G1 plus for consistency, U2 times G2 plus T1 times G1 is your Y. Very simple. So there is a real advantage of working in the Laplace domain compared to the ODE domain, because it tends to make things very uh, simple. So as I told, so these operations, if you are working in the ODE domain, they are non-trivial. So before we go further ahead, any questions? Any questions so far? I hope I am audible. Any questions? Hello. Am I audible, guys?
Yes, sir.
Yes, sir, you are audible.
Any questions so far? Is this clear? Some response would be helpful.
Yes, sir, good enough.
Cool. So now, so this kind of completes the first aspect. So what's first impediment what you have to overcome is how to deal with the issues that related with the OD. And the second is what would happen if you have non-linearity in the system. So that, as we have discussed earlier, that requires something known as linearization. So again, you are kind of assuming that the higher order errors are okay to handle because oftentimes they would be so they would only contribute to the overall performance in a marginal fashion. So we have to take a bold what you call step saying that okay, I am okay with the first order terms in the Taylor series, and the higher order terms, of course, would be there, and you would neglect. So how do you deal with such situation? You have a nonlinear model, and you would find a good approximation near an operating point. So this is a very key aspect. So the linearized model is only valid at the point. So let's say at the point of linearization, let's say you are this is your operating trajectory y versus t, or maybe y versus x, maybe whatsoever. So if you linearize, so basically what are you doing? You are drawing a tangent here. So this is what linearization essentially means, right? So this validity is only for this regime because the linearized model, let's say if I call it as one, example, and you have developed a model here again. You are drawing a tangent. So this model one will have a very different characteristic compared to model 2 because they have linearized at a very different points. So the model your so what essentially in process industries people do is if you have so most of the process industries would have fixed operating conditions. Nobody is going to play because they know that the yield for the product quality or product concentrations are fixed for particular operating points. So you know all these operating points and you develop these linear models only at those operating points. So you cannot have a global model. So global model is first. So if you have a model that represents the entire operating regime, so let's say all here, that's a global model. So whatever you're doing is a local model. So that will only have influence uh, or so its accuracy is only expected to be uh, good only at the point of operate. So if you have multiple operating points, what you should do is you should develop multiple such what you call linear models, and when your operating condition changes, you activate those. That's also a fair deal because it doesn't add up to the complexity. Okay, so now see how are you going to do it? Okay, so when you linearize an ODE dy dt is equal f of y comma u, the first term is the so you are linearizing at a point, okay, y bar u bar. So let's say if I write as this is u. So I will call this point as y1 bar u1 bar. This point may be y2 bar and u2 bar. So this operating point linearization done at y bar u bar for a general point. The first term is the steady state term f of y bar u bar. Second is derivative of f with respect to y at y bar u bar times y minus y bar. Third term is derivative of f with respect to u, which is the second variable, times u minus u bar. Plus, as we have told, higher order terms of the order of n square. Second order terms we are neglecting. And at the steady state, and at the steady state, okay, at the steady state, what would happen? Your y become y bar, u become u bar. So what happens? This guy would go zero, this guy would go zero. So at the steady state only, your constant term which is also sometimes people call it as affine term. It's just a constant. So people sometimes call them as affine term. Only affine term exists. Okay, so now coming back to our case, so our way is we should be able to do it in so our procedure was our model should be able to match the static and dynamic mode. So we will again do this subtracting business. Okay, 1 minus 2. So your this term, our bias, sorry, the affine term would cancel out. Okay. Y minus y bar, let's call it as y prime, u minus u bar, let's call it as u prime, and of course y minus y bar become y prime. So this is the linearized ODE, and we know how to deal with this linearized ODE. So any questions here before we move ahead? Any questions?
No, sir.
Are you all with me? Okay. So now next what we are going to do here is, so we look at some examples and how do you do it in real time. Maybe in next few slides, how do you develop a transfer function development by linearization. This is what our objective. So first, let us look at a case where the system is linear and not nonlinear. Okay. So this is the our simple system that we are going to look at. So there is a tank. Okay. If there is a feed in, you would see here. Okay, and there is a pump that drains out the flow from the pump from the tank, and height of the tank gets is varying with respect to time, and area A is the area of cross section of the tank. So what we should do, we should do a mass balance. This we have done in our previous tutorial also, similar problem. And so one thing you have to see here, that is that you have keeping a pump here. What is the advantage of keeping a pump? Can someone say? Unlike valve, so let's say this is a valve, and this is case A and case B. What would be the difference between valve and a pump? Someone can give. What would have the what would be the effect of outlet flow rate Q naught if I place a pump, or in contrast to if I placing a valve? Can someone say? Attempt at least based on your fluid understanding from the fluid mechanics.
Sir, the pump will increase the flow rate.
Okay.
And
Close.
we can adjust the valve to increase or decrease the flow rate accordingly.
Close match. Something more very precise. Someone can think. So you got the overall idea, but very specifically, there's a fundamental difference. Can someone think? Of course, you all be thinking. Can someone say? So your points are all well taken, but a few more. What I would say. Uh, mm, any thoughts? Okay, so I'll tell you one example. So if you are using a valve, the flow is essentially driven by the head. Because there is no mechanical pressure, only the head is what drives the flow when you have a valve. But if you have a pump, your outlet flow is independent of the head. Why? Because the pump is externally driving it. So you are not really worried about what is the head loss and things like that. Outlet flow rate would be mostly a constant because the pump would draw out the flow rate at its rated capacity. Agree? Is that clear?
Yes, sir.
So if you are using a valve, that's more of a head dependent outlet flow, while it's a pump. It's mostly a fixed rated outlet flow as dictated by the pump specification, assuming that there is no cavitation and so on and so forth. Because the impeller speed would take the outlet flow rate, unlike the change of head. While if it is a valve, you see that if the head is high, maybe the outlet flow rate may be high. When the head becomes low, the outlet flow rate may be low, which is not the case if you have a pump. Anyway, so let's say we have pump here. So mass balance is A into dH by dt, Qi minus Q0. And assume that at the steady state condition, it is Qi. Is the steady state condition of Qi is Qi bar. And Q naught, which is outlet flow rate, is Q naught bar, and which leads to this equation. Okay, not in this equation, in fact. So what I am trying to say is this is after the deviation. So here, so when you subtract this properly from here, you would get Qi prime, Q naught prime, A into dH by A into dH by dH prime by dt. I hope this is very clear. So we have done this exercise multiple times. I hope this is very clear. Any questions here? Can someone?
No, sir.
Perfect. Okay, so now what shall we do? This is an ODE. We should go to the Laplace domain. So A times S into H prime S. H prime S stands for the Laplace. Sometimes, as convention, generally capital letters are used if you do a Laplace transformation, but it is not necessary. So most of the time you might see multiple books, even you might see inconsistency in mine also. But it's a good idea to use capital or like the uppercase letters for the corresponding Laplace variable. If you represent the original variable in terms of lowercase variable. But here you see we are not doing that. So that's what I told. There may be some inconsistency you might see, but it's a good idea if you use it uppercase for a corresponding Laplace variable. Okay, so AS into H prime S, Qi prime S, Q naught prime S. Okay, so this prime stands for the deviation, right? So what happens if you are putting a pump? So Q out Q. Okay, so what would eventually happen if you use what I would say our pump? So Q naught prime, which is Q, just a second. Q naught prime, which is like Q naught minus Q naught bar will be 0. So I should put this Q naught bar. Because pump, there is always it draws the flow at a constant time. It doesn't consider if there is a what I would say steady state or unsteady state. If you switch on the pump, every time it would be a constant flow. So that essentially means that this time has gone out from your analysis. So your your simplified equations are as h prime s is equal to qi prime s. Okay, so now you wanted to isolate the figure out a transfer function that lies between h and q. H prime s by qi prime s is 1 by as. So here we never used a linearization, and we will see if you use a linearization, yes, in the second case. So this particular type of transfer functions are called integrator because it contains 1 by s. So if you look at the definition of the Laplace transfer solver, yeah, so a transform of an integral is 1 by s times s. So which essentially means that your original function is an integrator. So what does integrator means? Eventually what would happen? Your pump would fully drain out the flow, and so the profile that you would receive is like this. So let's say this is h, this is time, this is something that you would always see. Your head would keep on decreasing, decreasing, decreasing. It might go or might not go, that's to zero, that's a fine. After, as a function of t, this might keep on decreasing because the pump will draw out and the height of the tank would keep on decreasing. So any questions on this? Any questions so far?
No such clear.
Perfect. So now let's look at the case where you have a linearization term. So if you attended the tutorial in the previous class, we have learned something on a square root nonlinearity. So outlet flow rate of a valve. So now I am replacing the pump with a valve. You see, there's no pump here, but a valve. But outlet of the pump pump follows a square root relationship. CV is the valve coefficient, H is the head. So it is no more constant. It would eventually depending upon what I would say, the height of the tank. And if you look at our tutorial, we also have looked at a case where the outlet is varying linearly with time. So Q, so this Q naught. So again, I apologize for the confusion. So let me just put here. So let's look at the steps. Okay, so I will put a Q naught here. That would save confusion. And maybe here also I'll put a Q naught. So Q, read Q and Q naught are same. And QI is inlet. So both, so we are interchangeably using Q and Q naught for the outlet and QI for the inlet. So, so if it's just a linear relationship, so how do you calculate the flow rate? So the flow rate would be, so this is what we have learned in the tutorial, change a rate of change of head. So let's say this is rate of change of head, okay, divided by the resistance, like driving force, which is the head, and the resistance. This is if things are linear, but here of course it is non-linear. So if it is just linear, as you would really see, A into dH by dt qi prime times 1 by h 1 by r times h prime. This is when things are linear. So now let's see when things become non-linear, if q naught becomes Cv times root h. So A into dH by dt is equal to Cv times root h. So here there is some difficulty. So we may not be able to take Laplace transform as we have done previously. So we will do the Taylor series linearization on the right hand side. So if you see how did we do the Taylor series linearization, if you look at this expression, dy by dt would stay as it is. F of y comma u is what is going to be get expanded. So dy by dt is equal to f of y comma u would be f of y bar u bar df by dy into y minus I bar, df by du into u minus u bar. So the same thing applies here. A into dhi by dt stays there. Okay. So first is the constant term. How do you calculate the constant term, which is for the zeroth order term? So you evaluate them at the, so, and our linearization points, it's important, is qi bar and h bar. The zeroth order term is just substituting that value, qi bar minus cv times h bar of point h bar for 0.5. And of course, all right. And the first linearized term would be linearization with respect to the first variable, df by dqi times q minus q bar, qi minus q bar, df by dou f by dou h times h minus h bar. Okay, so now what you have to do is, this is of course a slightly simplified step. So we have to now see how dou f by dou qi, how do you calculate that? So here there is no problem, it would be just 1, because qi is only 1 here, so this is 1, so that's why 1 comes here. So this is ah prime, which means that the constant term you are subtracting, that's why 0 comes in here. And the second term is dou f by dou h. So that is a little tricky, not tricky, you will have to do a proper differentiation. So it would be it would be what you call, so qi would go 0, it would be minus cv times, okay, h power minus 0.5 evaluated. So this would be the derivative. So that's what comes in over here, h minus h bar. So that essentially means that this is qi bar, this is h bar, qi bar and h bar, half of cv times. So if this would be your simplified linearized equation. And if you compare this with your previous equation here, so h prime is right here. Here is h prime, here is h prime, and this is 1 by r. So this whole term 1 by r is this much. So which essentially means that r would be the inverse of that. That's what we have written over. Again, so this would, if you want to write in that what you call the driving force by resistance form, a into ds by dt, a into ds prime by dt, y bar minus 1 by r, where r is this times h prime. Any questions here at the moment? Is this all okay to you? Is okay? I hope there are no issues and it moving ahead. Okay, so now let's try to, so see this, see, now let's write that again, differential equation right here. So this is a differential equation that led between qi and h, you see, qi and h. So a into ds prime by dt, qi prime 1 by minus 1 by r times h prime. So take the Laplace, a into h of s, qi times qi bracket qi of s 1 by r times h of s. Here I have correctly put the uppercase letters to designate the Laplace variable. So So now you can do the rearrangement. All the h should come in one side and q should come in one side. So h of s times, okay, ar of s plus 1 will be r into q of s. So h of s by qi of s would be k times, just a second. I would say r times, it would be, so let me just write it like this. So r by ar s plus 1. So this ar generally I'll replace as t tau, okay, and r I'll call it as t. So just to make it as standard. So we will see there is a why we should write it like in this particular form. K by, so generally the standard term on the numerator is called as gain, which is represented by k. So here r stands for k and ar stands for tau. This is something known as the typical characteristic of first order system, which we learn. I'm sorry. And now let's try to draw the relationship between. So this is between qi and h. So inlet flow and the height. So now outlet flow and height. What is outlet flow and height? So the outlet flow and height would be it would be as simple as, so this term is something that stands for your outlet flow. So Q naught is equal to 1 by R times H prime. So I'll take that over here. Q naught is equal to 1 by R times H prime. So again, Q naught by Q naught s, H of s taking the Laplace, 1 by R stays there. And H s by, H of s by Q of s would be R, I have written it as 1 by k. H of s by Q of s is equal to 1 by k, which is equal to R. So then here should be 1 by R. Give me a minute then. H of s, let's check this, or there is some typo that I have made. So let's calculate H by Q. It would be R times AR S plus 1. Fine. So yeah. Q by H. Okay, so it's a mistake that I made here. Let me correct it. So this is absolutely fine. So this 1 by K. Hope I'm not confusing you. I'm just fixing this typo. So this is so essentially you please read it as Q naught by H of S by H of S, which is 1 by K. So any questions here? I'm sorry. Any questions? Anyone? Am I audible? Is that okay? All right. Any confusion so far? Can some of you could give a feedback, please? Ashutosh, Ankit, are you all there? Hello. Am I audible to you?
Yes, sir, you're audible.
Any issues so far?
No, sir, it's clear.
Perfect. So now we will talk one more thing and we will stop for today. So we have seen this integrating effect, not the integrating effect, the multiplicative property of transfer function. If you have two, for many your y would your output would be a linear. Okay, so if there are multiple transfer functions that are sequentially connected, the overall model or the overall transfer function is the product of all of them. So let's say instead of a single tank that we have done, we have you have done kept two tanks just to showcase this property. And now we need to develop the model between Q2 and Qi, which is the outlet flow rate of the tank 2 with respect to the inlet flow rate of tank 1. We can use this property to derive the model. So for instance, Q2 by Q1, I'm going to now simplify it. Q2 by Q1 I can, so let's say I'm going from here. So first of all, I am finding a transfer function between Q2 and H2. Okay, then I will find the transfer function between okay, H2 and Q1. Okay, then I will find the transfer function between Q1 and H1. Then I will find the transfer function between H1 and Q1. And we have now found the transfer function that relates inlet to outlet as k by tau s plus 1 and outlet and height as 1 by k. So can we write them that? So let me just, so I'm just multiplying them together. H2 by Q2 by H2, Q2 by H2, H2 by Q1 and Q1 by H1 and H1 by Q1. So what would eventually happen? All of this would go, this would all cancel, only Q2 and H1 would retain. And and we have now just found out for the tank 1, H1 by Q1 is K1 by tau s plus 1 and Q1 by H1 is 1 by K1. Similarly, for the tank 2, you will only replace 1 with 2. H2 by Q1 would be K2 by tau s plus 1 and Q2 by H2 is 1 by K2. So because it is the same system, only the tank has got changed. Only the values of K and tau is going to change, which is basically the product of A and R and R. The area might be different and the resistance may be different. So you can just multiply all of this together. So this is of course a starting. We would use this property in more detail when you reduce the complex models. So with this, I'll stop here, and if you have any questions, we can discuss. Otherwise, yeah, we will close today's class with this. So this basically helps you to scale up the system, scalability. So this is an important thing. You see, any modeling system should be scalable. So if you have made off-the-shelf model for all of this, you can you can very nicely connect or integrate them together to get the any complex model for any large scale system. So this you should appreciate could only be possible due to the in the Laplace domain, not in the ODE space. So you should appreciate the beauty of what is called simplifying the system by means of compartmentalizing. So it's easier to develop models for small compartments than the larger system, which is like an integration of all this compartment. It's either to use what you call multiplicative rule according to your condition, or additive rule, whichever the way your systems are organized. So this would help you to develop any complex systems model by kind of making their individual small slot model and integrating them. Of course, we will talk this in slightly more detail in the subsequent classes. So I'm just giving you a glimpse. Any questions so far?
No, sir, all on track.
Perfect. If there are no more comments, I will. So let's close the class and see you on Friday. Is that okay? Any issues?
Pardon me, sir?
So if there are no more questions, we shall close today's session and we'll see you on Friday.
Sure, sir.
Okay, guys, then bye-bye.
Thank you.